next presentation is temperature sensing in a UHV environment. It's sponsored by Zybex Lab.
Good afternoon. My name is Ward Parsons. This is Alan Whistler, Longman from J Law. This is our second semester of doing UTD design. In case you were here last semester, just need a memory jog. Let me recap what we had done. Zybex Lab wanted a temperature sensor to put inside their ultra-high vacuum chamber to sense the silicon target that they're trying to pattern with an STM microscope. The temperature is important because there's a fairly narrow temperature window that they can do this over. The sensor had to be within the chamber and able to withstand pressures down to 10 to the negative 11th torr without substantially outgassing. It also had to withstand the bake-out temperature of the chamber at 125 degrees Celsius. And when it's sensing the target, it would do this at 250 degrees Celsius without being in contact with it. It had to do all this while maintaining relatively good precision. Additionally, we had to find a way to actually put it inside the chamber, which is kind of strange. So last semester we found a promising sensor, ordered several of them, along with an instant bus interface to communicate with it and set about their interactions. Long and Jay here tested the UHV compatibility and survivability of the sensor within the chamber. They're able to pump it down to 1.6 times 10 to the negative 11th torr, which indicated no substantial outgassing, which is good. And after they removed it, it functioned as well, which was even better. Meanwhile, Alan and I worked on a LabVIEW virtual instrument to communicate to the sensor and log its readings. After we had done this, we actually took some readings of a large stainless steel plate with the sensor and simultaneously took readings with a K-type thermocouple attached to it. And after correcting for the emissivity of the plate, these agreed quite well. So these were very good findings from last semester, and much more than we'd hoped for from a $16 sensor. So this semester, we set out to see if we could actually use the sensor without infrared lens, because the field of view of the sensor is actually pretty wide at about 100 degrees. And the target they're using is a piece of silicon that's 9 by 7 millimeters, and it's at most going to be 2 centimeters away, so it doesn't fill up all of that. But first we have to verify a few things. The pressure readings from last semester seemed a little too good to be true, so we repeated that. And this time we were able to get it down to 2.1 times 10 to the negative 10th torr, which is very similar to last semester and almost identical to the baseline pressure of an empty chamber, which again indicates no substantial outgassing. Alan and I also needed to gain write access to the sensor so that we could provide for onboard emissivity correction, which we achieved. From this, with consultation with John from Zybex Labs, we set forth on a plan to measure the temperature of one of these targets at different distances, viewing angles, and temperatures. And to see if we could calibrate this to a K-type thermocouple, which was attached to the silicon target via a tantalum clip. We naively thought we would be done this very quickly and move on to UHV testing itself and put it in the chamber. This wasn't the case. When we started measuring, we ran into problems with infrared pollution from the surrounding room, along with temperature fluctuations due to air movement. Plus, just heating up the silicon using a power supply is pretty finicky here. Fingers have to be pretty precise. So, some of the best solutions are the simplest, or so they say. In our case, this was a box we put over the entire test setup, which blocked any instant IR and air fluctuations. Even with this, we found we had to let the system stabilize for about 20 minutes before it reached thermal equilibrium, before we could take measurements. So this is what we did all semester. Such is the humility of science, I suppose. Anyway, after we got this done, we were actually quite pleased with the results that we got. And there was a strong correlation between the sensor readings and the thermocouple readings. We found that the viewing angle, the angle that's positioned at the target, has relatively little effect on the graph, whereas the distance from it has a little bit more. But in any case, they'll be able to calibrate it with some of these positions. And the last thing that really has to be done, which will at least help start, is to see if what little outgassing might be coming from the sensor is in fact harmless or is a nastier accretive compound, which could interfere with their cap. It sounds pretty easy, but one thing we've learned is that it won't. So, with us, / good luck. I'd like to thank John Randall from Cybex Labs for all his help, along with Yushabal and Jeff Bayan here at UTD. Thank you. Any questions?
Can I ask a question, John?
You mentioned 4 centimeter under tested precision. Did you take any 4 centimeter data?
We did. It did not make it onto this graph. No. You can come by and talk to us about it.
Okay.
You said the positioning caused issues. Were there any vibrations in the systems that caused you problems?
We didn't know of any vibrations that were causing us problems. We had some real problems with thermal equilibrium though, because the holder for the silicon target is in part metal and it would heat up along with the silicon. And additionally, since the sensor was so close, it was actually heating up as well. And it uses its die temperature as a reference to calculate the temperature. So as the die temperature rose, its sense temperature would rise as well. So that's major.
You mentioned the resistor, but that's 9614. Is that what, like a TI digital sensor?
That's the infrared sensor that we were testing at MLX 906. It's made by glasses.
What was the biggest challenge that you had to overcome from senior design 1 and 2? Did Cybex, for example, change your design criteria?
No, they were actually, what we were most worried about was the precision that it was going to be at. We were under the understanding that it had to be very precise, less than 0.1 degrees. But as it turns out, it's precise to 0.3 degrees Celsius, which is good enough for their applications. And additionally, the setup of their chamber will make sure that it reaches thermal equilibrium. And from Seniors, anyone?
Yeah, I think the biggest difficulty we had in transitioning is we kind of saw our measurements from the first semester and we thought it was all going to be easy, taking the measurements and verifying that the sensor would work. And we weren't getting the numbers we hoped to get. And also, like you mentioned, the system heating up was a real problem for us. It wasn't something we were expecting. So when we saw, we're taking measurements and the thermocouple readings are steady, but our sensor temperature keeps going up, it's, something that you're not expecting that threw us off.
So you encountered things that weren't in the original design.
Yeah.
But you were looking at.
Well,
Yeah, this semester is much more tedious than
definitely.
And this is actually a very significant finding for us. I've got an external pyrometer that cost $4,000 and only reads down to 250 degrees C. If I can replace that with a $14 sensor that goes in the chamber that gives me room temperature up to the 300 degrees C that I want, that's a major win.
That's like a good cost-effective
Yes.
solution.
Yeah, no kidding.
Was there also an issue on reliability when you asked that?
There's going to be a long-term reliability issue that may come up that was really outside the scope of the work here. They showed very repeatable, they took great data, and actually worried more about the sort of 10th degree precision and non-contact measurement of silicon in a UHV environment. If I know the measurement within a few degrees C, I'm happy.
Well, thank you.